Namaskar students, today we shall start a video series about mean value theorems. Now the first question is, what are these mean value theorems? Mean value theorems are fundamental classes of results in differential calculus that describes the behavior of differentiable functions. Now there are three most common mean value theorems in the syllabus of undergraduate level in almost all the universities of our country. Rolle's theorem, Lagrange's mean value theorem and Cauchy's mean value theorem. Today in this video, we shall describe Rolle's theorem. So let us start today's video. So this is the statement of Rolle's theorem. What is it telling? It is telling that if f is a function from AB to R, what is the meaning of this AB to R? It means that the input of the function will be taken from the closed interval AB and the output of the function will be a real number. So f can be told as a real valued function. So if f is a real valued function such that these three conditions hold. What are these three conditions? F should be continuous in AB, f should be differentiable in AB. What is the meaning of differentiable? That is, the derivative f dash should exist in open interval AB. And the third one, which is the most important one, that is the functional value of f at the boundary points. Boundary point means the outskirt points of the interval A, B. So the functional value at the boundary points will be equal. If these three conditions hold, then it is telling that there will exist at least one value C in between the open interval AB such that the derivative of the function at that point C will be 0. Now, before moving on to the geometrical interpretation of this theorem, let us understand a few minute details of this theorem. Firstly, see, there are two parts of this theorem. The first part is called the hypothesis part, and the next part is called the result part. Why is it called the hypothesis part? Because if this theorem is to hold true, then the hypothesis or the first 3 points must be taken into consideration. That is, f should be continuous, f should be differentiable, and the functional value at the boundary point should be equal. Since these 3 points must be taken into consideration before proceeding into the result of this theorem, so this part is called the hypothesis, means the part which is taken into consideration. So the final part will be called the result. That is, if the hypothesis holds true, then the result will also hold true. Now there is another thing in which we must be very careful while seeing this theorem is the mixture of uses of open interval and closed interval in this theorem. Now see, the domain of this function is considered to be a closed interval. See, the significance of closed interval and open interval is that in closed interval the boundary points are within the set, and in open interval the boundary points are not within the set, they are outside of the set. So here the domain of the function, that is the closed interval AB, is taken, meaning that the boundary points AB are within the set, within the domain of the set. Now f should be, in the hypothesis part, f should be continuous in closed interval AB. So the boundary points are also taken into consideration. But while considering the differentiable part, see, we are taking the open interval AB. So f should be differentiable in open interval AB, that is okay. No need of testing the differentiability of f in the boundary points. If f is differentiable also within the boundary points, then f will be differentiable in closed interval AB, that is okay. That is beyond our expectation, but our expectation is limited only to f to be differentiable in open interval AB. And finally the part C. C will be a point that is to be found within AB. C will not be equal to either of A or B. See, because C is taken from the open interval AB, not closed interval. So C cannot be equal to A or B. So these are the first few considerations or first few descriptions, first few understandings that we must keep in mind while studying this theorem. Now let us understand the geometrical interpretation of this theorem. Now to understand the geometrical interpretation of this theorem, I have noted down the hypothesis and result part in the right hand side, and I have plotted 6 different graphs, drawn 6 different graphs to understand which type of graph actually fits into the hypothesis and the result part, that is fits into the statement of this Rolle's theorem. So let us try to understand which graphs fits in and which graph is discarded. See, firstly, f should be continuous in closed interval AB. In these graphs, these horizontal lines represent the x-axis and the boundary points are plotted over here, AB, 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 and so on. So f should be continuous. What is the meaning of continuity? That is, the curve will move in between A and B without breaking or without any point moving towards either minus infinity or plus infinity. See, for the first graph, we have the function at this point to break down. See, the function has broken down at this point. It has come from here to here. Then again, it has a jump discontinuity moving from here to here. So this function has a jump discontinuity in this part, So this function will not be useful for this Rolle's theorem, for the hypothesis of this Rolle's theorem. So this is discarded. For the next graph, see, it does not have any jump discontinuity, but at one of the boundary points, that is the B, it is moving towards infinity. So you will not get any real value at the point B. See, if you remember, the function f is from closed interval AB to R. So the function will take inputs from the closed interval AB, closed means including the points A and B, and the output will be a real value. So if you take the boundary point B, the functional value at the boundary point B is tending towards infinity, which is not a real value. So f will be considered discontinuous at the boundary point B. So this is also discarded. This type of graph also will not be taken into consideration for the Rolle's theorem. Now, remaining all graphs, see, there is no question of jump discontinuity like this or tending to infinity. So for these 4 graphs, the first hypothesis, f should be continuous in closed interval AB, is true. Now for the next hypothesis, f to be differentiable in open interval AB, let us see if this is true for these 4 graphs or not. Now what is the meaning of differentiability? Now f to be differentiable in between A and B means that there will exist a tangent at all points in between A and B. Tangent will be unique. Tangent cannot be multiple for a single point. Okay. See, for this graph, even though it is continuous, there are sharp edges, sharp points over here. At these sharp points, there you can construct multiple lines which cannot be considered as unique tangents. So, at these points, the function will not be differentiable, because differentiability means that at those points, you will have to get a unique tangent. So you are not getting a unique tangent at these sharp points. So function will not be differentiable over here. But for the remaining 3 graphs, see, since they are purely curves, smooth curves, you can get unique tangents at each and every point. You will get unique tangent over here, here, at each and every point. Only unique tangent you cannot get at discontinuous points like these and at sharp points like these. So this also is discarded because the differentiability part does not hold valid or true over here. Now the first 3 graphs are discarded because of first 2 points. Let us move on to the third point. The first 2 points hold true for the remaining 3 graphs, continuous and differentiable. What about these? This is telling that the functional value at the boundary points will be equal. That means at the boundary points, the heights of the function will be equal. See, at the boundary points, the heights to the function, what are the heights? Are these two equal? This is called fa and this is called fb, the height to the function from a. It is fa and the height to the function from b is called fb. See, the heights are not equal over here. So the third point that is not holding true or holding valid for these graphs. What about these two graphs? See, for these two graphs, fa, that is the height at this point a, and fb, the height from at b, see, these two are equal. Similarly, over here also, the heights at the point a and b to the function, to the curve, are equal. So the third point actually holds true for the last two curves. So the last two curves are perfect examples that fits into the Rolle's theorem type of curve. Now the question is, if this type of curve, forget about these four are discarded. If these two type of curves holds true in the Rolle's theorem hypothesis, then what will be the interpretation of the outcome geometrically? See, the interpretation is telling that there will exist a point C in between A and B such that the derivative at that point will be 0. Now, if you remember the theorem, it was written that there will exist at least one point C. So, there can exist multiple points like C where the derivative will be 0. When will the derivative be equal to 0? I have told before, derivative means the slope of the tangent. So, you have to find the tangent. If the tangent is parallel to the x-axis, then the derivative of the function at that point will be 0, because derivative of a function at a particular point means the slope of the tangent at that particular point. When will the slope of a tangent or a straight line be equal to 0? If that straight line or the tangent is parallel to the x-axis. Over here, if you see these two type of curves which fits into the hypothesis, it has a point like this, like a mountain like this, top point, where you can draw a tangent which will be parallel to the x-axis. Similarly, for this type of curve also, where you can find a minimum bottom point, where if you draw a tangent, that tangent will be parallel to the x-axis. Always it will happen. You can think about any curve which fits into these three criteria simultaneously. That is, it should be continuous, it should be differentiable, no sharp points, and the functional value at the boundary points or the heights at the boundary points will be equal. If that is true, then the function or the curve will be such that it will have a point where the tangent will be parallel to the x-axis, like this type of curve which is like a mountain, and this type of curve which is moving downwards and coming up. Also, you will get a point at the depth where the tangent will be parallel to the x-axis, and the tangent, if it is parallel to the x-axis, the slope of the tangent will be equal to 0, which is nothing but the derivative of the function at that point. Now, why did I say there can exist multiple points or at least one point C? See, the function can be like this also. Instead of only one point, the function can be like this also. It is not a sharp, but it is curved. Okay. So if it is like this, see, the height equal, that is fa and fb are equal. It is continuous. Since it is smooth, it is differentiable at all points, and see at these points the tangents are parallel to the x-axis. So at these points C1, C2, C3, at all these 3 points the derivative of the function will be equal to 0. So this was the description and geometrical interpretation of Rolle's theorem. In the coming few videos, we shall describe the Rolle's theorem further more better by citing some examples, and after that we shall move on to Lagrange's theorem and Cauchy's theorem. If you have liked today's video, then do share this video with your friends, subscribe to my channel and follow my page. Till then, goodbye.